Transport modelling is a mathematical representation of the way the traffic flows. It uses software to investigate the effects of design decisions before they are implemented in the real world, and is an important part of the decision-making process in transport planning.
This allows transport professionals to explore and estimate the consequences of transport policies, strategies, or schemes using software rather than in a real network. This video introduces the three main types of traffic model and the role they play in helping us to understand traffic behavior.
Let's begin by considering a simple case study of heavy peak period congestion, which occurs on a busy road through a city centre. In this diagram, O shows the origin, with D representing the destination. To reduce the congestion, the solution might be to widen the road to the south, to increase its capacity. Initially, this seems an obvious solution. Within the first few days or weeks of widening, the same volume of traffic would travel more freely, reducing journey time. However, as drivers using the route to the north become aware of the widened road, it's likely that they will begin to use the southern route instead. As a result, this route would soon become congested again. In addition, this induced traffic would have knock-on effects on surrounding roads. The case study is an example of why mathematical modelling is required in transport planning. Mathematical models are a simplified way of viewing reality and are fundamental to how transport professionals understand, analyse and design transportation systems. The transport system is a combination of components which can be modelled using a collection of assumptions, physical laws, behavioural hypotheses and relationships. They also combine these assumptions with data specific to the situation being analysed. Consider an existing road network. At low volume, traffic can move at high speeds. However, as traffic increases, vehicles start to influence each other. As a result, the presence of other vehicles causes drivers to decrease their speed. This behaviour can be measured, recorded, and then used to predict traffic flows and where and when congestion might occur. Transport modelling varies significantly in format and complexity. The choice of modelling method depends on three factors: the purpose of the exercise, the level of detail, accuracy and certainty required, and the resources available. There are three levels of modelling which are applied to transport. Micro, focusing at an individual vehicle level. Meso, examining flows of transport on network links. And macro, looking at larger areas and associated travel demand. Let's have a look at each of these in a bit more detail. Microscopic simulation models transport systems at an individual vehicle level. The simulation moves these vehicles through a network. Here, the vehicles have their own characteristics and respond to the presence and behaviour of other vehicles and to traffic control devices. The primary limitations of these microscopic simulation models are the available computing power and the requirement for extensive data on road geometry and traffic control being available. Today, microscopic simulation models are used extensively in transport planning. While they are limited in geographic coverage, they are useful in analysing the key, usually bottleneck roadway segments where the movement of individual vehicles needs to be represented. These models, coupled with instantaneous emission models, have the potential to assess the environmental impacts of infrastructure improvements, traffic management strategies, and technology implementations. Here at the University of Leeds, we have developed our own microscopic simulation models, Dracula. There are also other models available to transport professionals, such as Visim, AIMSUN, and Paramix. In contrast with microscopic simulations, macroscopic models focus on the overall travel demands for a defined area and examine key measures such as system capacity. They were developed to describe the overall traffic flow within the network and not the movement of individual vehicles. Mesoscopic transport planning tools represent the flow of vehicles on a network link, but do not represent individual lanes. They are used to represent congestion conditions and temporal effects more accurately than macro models, but cover a larger geographic region than microscopic simulation models. Macroscopic models are based on the logic that most urban congestion occurs at intersections. However, macro-level models are difficult to use if very specific traffic control plans are implemented, or a better understanding of queue formation on specific road links is desired.
Here at Leeds, we have developed Saturn to perform macroscopic simulations. Another example used by the industry is the Vism software. All of these models provide the opportunity for transport professionals to analyze traffic flow. The use of these models also gives them the ability to test individual scenarios and to see the effects before putting them into practice.